Hello everyone, my name is Mia John, and I'll be presenting CUDA for Northwestern cs358 final projects. So here's a quick recap of CUDA. So as Professor Hamel mentioned during one of the lecture, CUDA and GPU is essentially the representation of modern SIMD, and it's SIMD on a massive scale because modern GPU typically has hundreds, thousands of cores. And CUDA is a C-like language that expresses programs that run on the GPUs for computation purposes. So here is some basic CUDA syntax. On top, we have host code, which is the code I'll be running on the CPU. And here you can see the threads per block, um, which is something that we have to define in order to launch a kernel, and I'll discuss it in more detail later. And then we need to define the number of blocks for which we want to launch in the kernel. And just FYI, well, kernel in this context is basically a function that will be running on the GPU. And here we call the kernel square vector, passing into a number of blocks and threads per blocks, along with the parameters to the kernel. Then we can go to the device code, the GPU code. Here's the function signature for the kernel square vector. As you see, there's this global declaration, and this essentially means that for this kernel, the entry point is from the host code, the CPU code, and then it will be executed on the GPU code. So in this code, it essentially computes the index of the thread, and if thread is less than the length of the vector, it computes square up on the input vector element and then store that in the output vector element. And square, and here's the definition of square, which is also a kernel. But as you see, square is defined with this device declaration. And this means that this kernel will only be called through, only be called in the device code. So it cannot be called from the CPU code directly. It has to be called from the other kernel. That's, I think, has to be also defined as global. And one thing I'm missing here is that in CUDA programming, another thing that programs need to care about is the transfer of data from the CPU to the GPU and from the GPU back to the CPU. And people tend to do that with CUDA malloc and CUDA mancopy. Then I'll talk about the GPU architecture for a bit, and the GPU that I'll be talking as an example will be NVIDIA GeForce RTX 3090. So as you see in the diagram, so each of these are what they call streaming multiprocessor SM. And in this GPU, there's a total of 82 SMs. And as you see in the middle, there's this big one L2 cache. And then it contains it's a storage for 6 MB. And one thing to know is that there's almost no F floating point 64 processing unit in consumer and non-data center GPUs. So for our GPU, it has two FP64 per SM versus 128 FP for FP32. And what this really means is that the floating point 64 computation will be much slower compared to the floating point 32 computation. And in order to write performant code, it's necessary to offload the more compute intensive section to the RPS 32 processing unit and only have the more critical section that is necessary to ensure correctness to be computed on the FP64. So I'll talk a bit more about streaming multiprocessor SM. So each of these blocks are what we call streaming processor. So which call also SP or CUDA core, but called by some other people. And it can be FP32 or INT32 for floating point or INT computation. And each thread will be running on one of these blocks. So as you see, so every 32 thread has a shared instruction fetcher. So what this means is that at the lowest level of parallelism in GPU, 32 threads will be executed in parallel by executing the same cell instruction provided by the fetcher. At the bottom here, we see SFU units, which contain some non-basic math operation, such as square roots, sine. And here we also see some LDST, load store units, which is responsible for reading and writing data between register and memory. And lastly, at the bottom, we see this um, storage that contains 128 kilobytes and is shared between the L1 cache and shared memory. So now I'll talk a bit more about the thread hierarchy and CUDA programming. So as you see previously, to launch a kernel, we need to provide a block layout, which is basically the number of threads in the block, and the grid layout, which is the number of blocks. So threads that are executed within a block are shall be executed in parallel on an SM, but as a programmer, you really don't know like which SM it's executed on, and you really don't know when does it get executed. So in order to make sure the order of computation follows what you will imagine, it's necessary to use implicit deck functions such as sync threads sometime to synchronize your threads. And another unit of computation is reps. So as I mentioned previously, these threads are really executed in a unit of 32 threads, which we call reps later on, also in this lecture. And also this is proper CUDA syntax, I believe. I'm pretty sure, yeah. So blocks are executed in reps and on a fixed processing unit in the SM. And And the reps that are assigned simultaneously take turns to execute, but unlike CPU, where the register will be pushed onto the stack, the register value will be pushed onto the stack, and the register are really used by another thread when you context switch in GPU. The register are reserved. So when the thread is not executing, the register are also not doing anything, any computation. And this is really an architectural decision because on GPU has a lot of registers. And we will talk about the implication of this in more detail later down in the presentation. So here's a simple diagram from actually a famous paper named Flash Attention that touches upon the memory hierarchy in GPU. All the number does not match the RTX 3090, but provides a basic idea. So in the GPU SRAM, which is the GPU shared memory, the bandwidth is 19 terabyte per second, and then it drops significantly at the HBM, the high bandwidth memory, which is the GPU global memory, to 1.5 terabyte per second, and then it drops significantly even more when we hit the main memory, the CPU DRAM, which has a bandwidth of 12.8 gigabyte. So this really means that we need to write hardware-aware CUDA code in order to make the CUDA code performance. And one way of doing this is to manually manage the shared memory via the shared variables. So here's some more hardware detail. So it takes 19 seconds for store, 23 seconds for load in L1 and shared storage versus for L2 cache, it takes 215 instruction cycles and global takes 300 to 600 instruction cycles. So shared memory is really this parallel memory architecture where multiple threads can actually access its data at the same time. So this shared memory is divided into units called banks, and each bank gets 4 or 8 bytes wide depending on the configuration of the architecture. So as long as each thread is really accessing a unique bank, then there's no conflict, and we can really leverage the parallelism in the shared memory. Otherwise, otherwise they have to go in some sorts of order. So now I'll provide a quick code demo on how to use shared memory to optimize to optimize the reduction implementation. So here we have a naive reduction implementation, which as you see, first we basically find the index of the thread or the position of the thread, and then if it's less than the length of the input vector, we do an atomic add operation of the element accessed by the thread ID in the input vector, and we add that to the op variable. And atomic add is necessary because all of these threads are accessing all at the same time. So if we don't synchronize it, then it will result in some force or race condition as they will see different state of the out variable. So first we have to use atomic add, but this is really inefficient because this means that this is inherently serialized in device memory, and we're not leveraging the parallelism that our GPU provide. So here in our optimized version, we we basically so in this optimized version, we basically do a two-phase approach to the problem. So first, each block reduce a subset of the input into shared memory, and then we add the result back to the global variable. I'll go in more detail in the code. So basically, first here we allocate a shared memory buffer for this block called as data, which will store the per thread partial sum before being reduced cooperatively down in the loop here. And for each thread, it will basically it will basically access two elements within the input vector and then store that in the partial sum and then store that into its thread ID. Elements, thread ID index elements in the shared memory data buffer. And then we reduce the array cooperatively using a tree-based algorithm. What's happening here is that each thread in the active range adds a value from neighbor's thread position ahead. And then we have the strike each time. And then during each steps, we synchronize the thread to avoid race condition. And this approach works pretty efficiently when block size is a power of two, which means that avoids the shared memory band conflict I mentioned previously. And ultimately, at the end, the thread zero of each block perform an atomic add to a single global variable out. And this out ultimately accumulates the partial sum. And while atomic add is so necessary here because these threads are all accessing this one global variable, but there's only one thread each block that's really doing the atomic add, doing the serialized add. So we really are cutting down the contention in the code. Um, I have provided, I have wrote the program, and here's a quick demo of it. And then yeah, I'm running it on Dubliner. So if we actually do the computation, you see the optimized version has achieved a 19.7 times speed up compared to the 9E version. So this really proves the point that in order to write performant GPU CUDA code, it's very necessary to leverage shared memory. So another major component of SM is its register file. So on the SM in total, there's 64 K32-bit registers shared between the threads. And these are really dynamically allocated within the block. This diagram is a bit misleading because it says like it's partitioned evenly into 4 register file, but that's really not the case. And register are threads private, unlike shared memory. So each thread really holds its own register. And this really brings into the idea that there's another parallelism involved exists beyond thread level parallelism that we are pretty accustomed. It's called instruction level parallelism. And this example will kind of provide a sense of what instruction parallelism really is. So so for this two lines of code to execute, first we do a sum from xi times yi, and then xi equals 10 times xi as scaling the x vector. And then if the register allocation is that R3 holds xi, R4 holds yi, and sum in R2. If we only have 4 registers, then you see that we're using R1 for 2 different operations. So we're using it both for the dot product and also the scaling. So this is because, yeah, as you see in this side, we really can't optimize it more to distribute the register better because this is we're hitting the limit. We only have 4. And what this is causing is that the second mu must wait for the this add to finish before it can execute. But if we just add one more register, now since R1 or R6 are just two independent registers, we can do the multiplication concurrently here, I mean in parallel here. And since they don't conflict with each other, and in the second steps, these two um, operations can also happen in parallel because they're independent. So by basically adding one more register, we're really able to parallelize the instruction execution much more. So its implication to CUDA programmers. So in NVIDIA's GPU's best practice guide, it says that increasing occupancy beyond a certain point yield diminishing return. And this really means that so when you have way too many threads, the register per thread decreases as it's hitting the register file limits. And so the speed of each individual thread will diminish. And in 2010, there's a study that shows near peak performance at very low occupancies by exploiting ILP. So this person is basically try hitting 100% utilization with less threads, but just with more ILP, meaning like more independent instructions. And he realized that in 2010 GPUs, if you have four independent instructions, you can easily scale up to, you can easily get to 100% utilization with fewer threads, but this does not scale beyond ILP equals 4. So how to really leverage this idea is that as we know, the memory bandwidth of GPU is typically limited compared to its compute as well as transistor are spent on its compute unit. So this means that the load instruction normally have high latency. So at the left, if we are trying to execute these four instructions, this math instruction has to wait on the load instruction first. And then this means that this load instruction has to, so this means wait until this math instruction, and this math instruction has to wait again on this load. So this is really just increasing the latency. As on the right, a more optimized version is that we can actually fire off the load at the same time. By doing so, we hide the latency of the load. And after we get the result from the load, we can do the math operation on the respective data and also in a parallel manner. So this will again speed up the code. And this is something that's really not handled by the programmers themselves, as the compiler typically would do this differential optimization. Um, and the compiler, so basically the MVCC, the CUDA compiler's backend, PTX-AS, it will perform instruction scheduling. So what it does is similar to what was illustrated here in LS batching. It will try to cluster all the loads together. So it will try to execute all the load at the same time at the start. And when you get the data, it will be able to execute all the operation on the data in the parallel manner if they're independent. And thank you. That's it. That's it for my final presentation.